So FTC means Fundamental Theorem of Calculus, which is a big deal, okay? Hence the name Fundamental Theorem of Calculus, okay? Or, like I said, abbreviated FTC. Fundamental Theorem has two parts, and the primary reason that it's such a big deal is what it does is it connects the idea of an integral, which we will find involves an antiderivative, something we haven't really talked about yet, to a derivative. So the two big branches of calculus are differentiable calculus, meaning things about instantaneous rates of change and applications of rates of change, everything we've been talking about prior to this chapter, and then integral calculus, which means the accumulation of a rate becoming an amount and the applications of that. What can we do with that? And this fundamental theorem ties those two ideas together. Okay, so in these notes right here, we're not going to go through the proof of the FTC, but I am going to attach another video, or I think there's two videos, and I'm just going to pull from Khan Academy because it does a great job of explaining it, but that will explain the proof of the fundamental theorem. We don't always go through proofs of things just in the interest of time, but you know that it's important to me that we understand why things work and why things have the relationships that they have and what conclusions we can draw. So I don't want to just say, here's the theorems, use them. I want you to make sure that you are understanding that big piece. So again, the big reason that it is a fundamental theorem is that it connects the idea of a derivative and to the idea of an integral. Okay, so what are the two pieces? We have a function f, lowercase f, that matters, that is continuous on a closed interval, okay? So g of x, a new function, is defined as the integral from a to x of f of t dt. So before we keep going, what does this mean? This number this value right here, the bottom limit, remember these two are called the limits of the integral, of a definite integral, that one has to be a constant, okay? It can be 0, it can be 5, it could be negative 3,000, doesn't matter. But we have an integral from a constant to a, and then this one up here is a variable. Okay, so let me stress that. We have a constant down here, we have a variable up here. G of x is a function in terms of the variable x. Okay, so g of x is not a numeric value, it is a function that represents the integral from a constant, so from some set starting point to any value of x of f of t dt. Well, we already talked about in the last section how the integral, the definite integral, finds the net area under the curve, okay, takes the area above, subtracts the area below. And so this is saying for any value of x, okay, the accumulated net area from some constant a to that point x is equal to g of x. Okay, and we'll see graphs and such in a minute of this, but that's what that means. Okay, so what's the conclusion of this? If g of x is the integral from a to x of f of t dt, then g prime of x is equal to f of x. In other words, the derivative of this function is the value of the function on the inside. Let me say this another way. This is called an accumulation function. Okay, so g of x here is an accumulation function. Okay, and what it does is it collects area as x moves from a to any value of x. And then this statement, this conclusion says the rate of accumulation is equal to the function being accumulated. Okay, so in words, the rate of accumulation is equal to the function being accumulated. Okay, because the derivative of that accumulation function is equal to the value of the function on the inside. Okay, and again, we're going to see examples of this in action in a bit, but let me talk about the second part here. The second part of the fundamental theorem says that the definite integral from a to b, so notice this is different because now these are both constants. Okay, so this is now numeric as opposed to a function like g of x. So the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of lowercase f, okay? Or in other words, the derivative of capital F is equal to lowercase f, okay? Antiderivative is a pretty new term for what we've learned so far, but we're going to do plenty of example of those in these next several sections, next couple chapters actually, okay? But the idea here is that capital F is an antiderivative function, but we are evaluating that function at number b and at number a, and we are subtracting, okay? All right, so let's look at some application and some common problems here, and hopefully this will stick a little bit better. Okay, so the definite integral of a rate of change, capital F prime, okay? So remember, capital F is the antiderivative function. So the definite integral of a rate of change, so if there's a rate function on the inside of an integral, we get the net change in the original function f, okay? So written a little bit differently, because remember up here we said capital F prime is equal to lowercase f. So if we put capital F prime on the inside, that's the same thing as lowercase f, okay? Then we integrate that and we get the value of capital F at b minus the value of capital F at a, which again is just a restatement of number 2 here, but here's the way that it frequently shows up. And I'll tell you right now, this is called AP's favorite formula. I'm going to abbreviate FF. So APFF, AP's favorite formula, because this shows up so often on AP tests, okay? And that is capital F of B, so if I isolate this, is equal to, so I would add capital F of A to both sides, capital F of A plus the integral from A to B of capital F prime. Okay, so what are we saying? Capital F of B represents an end amount. Capital F of A represents a starting amount. And then the integral from A to B of capital F prime of x is equal to the net change between A and B. So in other words, this could be something like, I know that the function R of t represents how fast water is leaking out of a bucket. And I know that at time 0, there were 26 gallons in the bucket. How we want to know how many gallons are left in the bucket at time 6. So then we could say, well, the original amount was, I don't remember what I said, 26. So the original amount, starting amount here would go here. This is the part I'm looking for. And then we would integrate from 0 to, I think I said time 6, from 0 to 6 of whatever that rate function is. Okay. And then I would evaluate that, add those, I would get the net change, but then I would have to add it to the original value, and then that would give me the ending amount. Like I said, you're going to see several examples of this, but this is just a restatement of the second fundamental theorem. Okay, so let's look at some of the things, the information we can get from the fundamental theorem. Whoops, kind of move things around here. Okay, this is example 2. We're going to come back to this. Example 1 just did not fit on the page when I was printing them because this one was a screen clipping. Okay, so go down to example 1 first. All right, so we are looking for net area. Okay, we talked in the last section about how a definite integral finds net area. And then here in the first part of the fundamental theorem, we defined a function g of x as an accumulation function if it goes from a constant, which this one happens to be starting at 0. They don't always, but this one does start at 0, and goes to x. Now, you may be wondering, why is there a t in here, a t and a dt instead of an x? That variable on the inside of an integral, it's sometimes called a dummy variable. We don't really care what the letter is because the output of the definite integral is either going to be numeric or it will be in terms of whatever variable we see here. So notice that this is g of x, which is a function in terms of x, okay, not in terms of t, even though the function f on the inside is defined as a function of t. Okay, so again, g of x is a function, not a numeric value, but we are going to evaluate g at some specific numeric values. Okay, so what are we looking at? This first one says g of 0. Well, if I plug 0 in for x, again, function of x, not function of t, I get that g of 0 equals the integral from 0 to 0 of f of t dt. Okay, well, we don't really need to hop over to the picture here. The integral from 0 to 0, in other words, the net area accumulated from 0 to 0, well, it's not going anywhere, so that is just 0. We will talk more about properties of integrals in a later section, but this is one to notice that if we go from a number to itself, the value of that definite integral will always be 0 because there is no space or no interval over which to accumulate any area. Okay, and then g of 1. G of 1 says, if I plug 1 in for x, g of 1 equals the integral from 0 to 1 of f of t dt. Okay, so what are we looking at here? Now we're saying from 0 to 1, how much area has been accumulated here. And we can do this geometrically, just like we did at the end of the 6.3 notes. So this is a 1 by 2 triangle, so that is going to have an area of 1. Okay, 1/2, 1 times 2. For this one right here, for g of 2 is equal to the integral from 0 to 2 of f of t dt. Okay, so now it's the area. We already said that has, I'm going to label it actually with a 1 instead of filling it in here. Okay, so this has an area of 1. And then now we are adding this space right here, which is a rectangle that's a 1 by 2, or yeah, 1 by 2. So 1 plus 2, we have a net area of 3. Okay, and you can kind of see how this is going here. G of 4 means we're accumulating all the way to 4. So let's see, what is the area of this shape right here? Well, it does tell us that this function consists of 2 line segments, okay, that this one, and then 2 quarter circles. Okay, so it is a quarter circle right here, okay? That's a quarter of a circle with a radius of 2. Area of that would be 4 pi, but only 1/4 of it, so this has an area of pi, okay? So g of 4 is equal to the integral from 0 to 4 of f of t dt, which is equal to 3 plus pi. Okay, and then g of 6 is all of that, but now this also has an area of pi, okay, same size quarter circle, but remember that the definite integral subtracts any area that is below the x-axis. So these two will cancel each other out, essentially, and we end up with just 3. But let me write it out. Okay, so the integral from 0 to 6 of f of t dt is equal to 3. Okay, again, it's not negative area. It's that the definite integral subtracts the area below, and so pi minus pi is 0. Okay. These 3 are a little bit different here. G prime of 1. This is asking for the derivative of the accumulation function, okay? Well, the first part of the fundamental theorem, let me scroll back up here, says that the derivative of the accumulation function is equal to the value of the function that is being accumulated. In other words, g prime of 1 is equal to the value of the function on the inside, which is f, okay, that's what I'm looking at, which is f at x equals 1, okay? And f of 1 is 2. So again, the value of this function that we're looking at, which at x equals 1 happens to be 2, is the same as the rate of change of the accumulation, okay? And then g prime of 4 is equal to f of 4, which from our graph is 0. And then for g prime of 6, that's going to be equal to f of 6, which is, f of 6 is -2, okay? And then for this last part here, it says sketch a possible graph of g in the coordinate plane provided. And it does give us a hint to find values of g double prime that can, oops, don't move that. That can tell us about some concavity, okay? Let's start with what we have, though. We're looking for graph of g. We have a bunch of ordered pairs. This is the point 0, 0. This is the point 1, 1. This is the point, oh, this is convenient, 2, 2. This is the point, all right, this one's not linear, 4, comma, 3 plus pi. All right, gets a little bit funkier there. And then g of 6 is the point, so that's point 6, comma, 3. Okay, but those are points that we can graph. So we have a point at 0, 0 on g. We have a point at 1, 1. We have a point at 2, 2. Okay, and then we have We have points at 4 comma 3 plus pi, so that'd be 6.14. So 4 comma 6.14, just a little bit above there, and then 6 comma 3. Okay, now we can't just connect all of this linearly, which is why it's also telling us to look at the second derivative. We do know the slopes at some other points. Oh, did I miss? Wait a second. 4. Yeah. Okay, so I do know at x equals 4, g has a slope of 0, meaning we've got a horizontal tangent there. At 1, we have a slope of 2, so I'm going to put just a little tangent line there. Let's see, at 6, we have a slope of -2, something like this, but let's figure out what's going on in between there. So g double prime would be the rate of change of the function g prime, which is equal to f. So g double prime of x is equal to f prime of x. Okay, and then so let's look at the derivative here. From 0 to 1, f has a slope of 2. So that means, so let's say on 0 to 1, f prime is equal to 2. So on 0 to 1, we have a slope. Oh, how am I going to get a slope of 2 there? Oh, my bad. That's not a slope of 2. So f prime would be g double prime. So that's concavity. So that tells me that we are concave up. The slope is increasing from a slope of 0 to a slope of 2 because the value of the f function increases from 0 up to 2. Okay, so from 0 up to a slope of about 2. And then on, let's see, and then our slope stays the same at 2 on 1 to 2. So it's not totally drawn to scale, so my 2 should be a little bit flatter. So then its slope stays the same. So we should have a linear piece here. Let me kind of fix this. So we have a curve. Nope, too steep there. Curve, and then a linear piece. Goodness. Curve, and then a linear piece. And then, let's see, then what happens here? So now the function f starts decreasing. So from a value of 2 down to a value of 0, meaning my slope goes from 2 down to a value of 0. Also, the second derivative of g would be the slope of the f function, which is 0, starts at a slope of 0 right here, and then decreases. Okay, so that means we are concave down. So we're going to have a sharp turn here, and then concave down, and then up to, so the slope is positive, or positive 2. This should be a little bit smoother right here. Whatever, something like that. Okay, and then decreases down to there. Okay, not drawn super well to scale, but something kind of like that.